Hey, welcome back. This is now 9.7. We're going to start connecting the dots between these series and functions. Okay, so it'll turn out that we can kind of create a series to represent functions so long as it has a bunch of derivatives. And you, believe it or not, you've kind of already done this process whenever you've done an approximation, a tangent line approximation. So maybe we could start with a recollection. So recall this process. Maybe you're given some sort of function, f of x equals, and we'll keep it real easy, just e to the x. And we want the tangent line approximation at some point, we'll say 0, 1. Right? Okay, so what does that mean visually? Well, here's the curve y equals e to the x. And then we want to get a tangent line at this point, 0, 1. And my graph isn't drawn very well, but there it is. Okay, that little red line there would be your tangent line approximation. Okay, so how do we get that? Well, we're going to need the formula y minus y1 equals m times x minus x1. Let's rewrite it a little bit. So this will be y equals y1 plus m times x minus x1. In order, we got a point, right? So the x1, y1 is sitting right here. I can just plug that into the equation. And we need a slope. So how do I get the slope? Well, you take the first derivative. That gives you the slope of the tangent line, right? So f prime of x is e to the x. I want to find the slope at the point 0, 1 for my tangent line. So you just plug in 0 and get out 1. So plugging that information in now, so this will be my slope. I'll have y equals y1, which is 1, plus 1 times x minus 0. And so our tangent line approximation is 1 plus x. Okay, okay. What we're going to do now is just kind of amp this procedure up. So the procedure we use will give us this equation here kind of as your first approximation of the function. And then we're just going to start tacking on more and more stuff, and you'll see it kind of builds a series. Okay. For now, we're not going to let that go to infinity. We're just going to have maybe a polynomial approximation. So, but you can kind of see, well, if I just extended this infinitely, I would get one of these series things. Not quite a series. The series we've been studying have more or less been numerical, but now we're going to have variables involved. So, I mean, it's a consistent motif all throughout mathematics. You start with adding numbers together, and then eventually you add in variables and so on and so forth. So hopefully this isn't too shocking, but anyways, here we go. So how am I going to take this up a notch is basically what it comes down to. By the way, this is 9.7 on Taylor-Maclaurin polynomials. Okay, so how do I do this? What's the construction process? So there's some things I want, right? And you could, a lot of the craziness of mathematics, you know, why is there a pi in here? Why is this here? Why is just, believe it or not, from the initial constraints. So I think especially when you're doing in some probability and statistics areas, the constraints, like, you know, the area under the curve has to equal 1, will cause you to have certain types of functions rearing their ugly head. So anyways, the constraints here, we want, first off, the value of the function at some point, f of c, to equal this thing we're using to approximate it with. So f of c, we want it to equal p of c. So in this first example, you know, our f of x is the e to the x, and then our p of x was this polynomial approximation right here that we created, 1 plus x. And the point, that c value, is this 0, okay? So I note f of 0 equals 1, and then likewise, p of 0 will equal 1. So I want that behavior to happen. On top of that, I want all the derivatives to coincide. And what does that mean? That just means basically we want the same shape from both of our objects. So we want not just the derivative of the polynomial to equal the derivative of the function, but we want that. This is how we're going to take it up a notch. We're also going to want the second derivative to equal the second derivative here. We're going to want the third derivative to equal the third derivative here. And carry that process on all the way up to the nth derivative if we're trying to construct an nth degree polynomial approximation. Okay, so we'll want that to equal the nth derivative of the function, and all evaluated at c. Okay, so let's put this into practice here with an example. We're going to just work with the same function, this e to the x function, and then take it up a notch by producing a fifth degree polynomial. So the degree that we used in this first kind of recollection example, this is degree 1, so I'm going to put p sub 1. But in general, if you want a higher degree, you're going to have to notate that somehow. So we're going to put a little subscript. So in this example, I want a fifth degree polynomial approximation for the function f of x equals e to the x. And then I'm gonna have to talk about a center. That's that c value that I'm using. So in my first example, I wanted it centered right there at 0, x equals 0. I'm gonna do the same thing here. Okay, center at c equals 0. Okay, so how do we do this? Well, we're going to kind of just produce, I guess it's almost a system of equations. It's a little easier than dealing with a system. Like usually it's a little more work, but you're going to look at the function and its derivatives, evaluate those at this point c, and then make this system of equations from step point 2 above. This p prime of c is f prime of c, etc. And then we're going to be able to solve out for kind of the unknown coefficients of the polynomials. So it's a lot of writing at first, but you'll get used to it. So here we go. And this one is pretty easy because the function is always the same. The derivative doesn't change. And we have to go up to the fifth derivative because we want a fifth degree polynomial. Okay, and you'll kind of see, why is that here in a second. Okay, I'm also going to need to evaluate all these at 0, so they're all going to be 1. Right, so 1, 1, 1, 1, 1, and then write out your polynomial. So we don't know what the polynomial is, but we can just write it abstractly, right? So like I'll say the constant term, and I'm going to list it in ascending order of degree. So I'll put the constant first, and then a1x plus. And so what will happen is that I need to solve for this a0, a1, a2, a3, a4, and a5. And yeah, this is going to be a bit annoying, but you'll see we'll streamline the process and kind of get a formula out of it that we could use in general. Okay? It's not going to be, fun, but it'll be a lot easier than this example. This is kind of just brute forcing it here in the beginning so we can see a pattern. But anyways, taking the derivative, the constant a sub 0 is 0. The derivative of a sub 1x is a sub 1. Derivative of a sub 2 x squared is 2 a sub 2 x, and so on. Okay, the second derivative. And one thing that you'll find handy for this type of work is not to multiply out constants, because when you multiply it out, it obscures the pattern. Okay. Oops. And we are in the sort of we need to find patterns a lot in this section. P sub 5, third derivative. And we could replace 3 times 2 with 3 factorial. It's the same thing, right? 4 times 3 times 2 is basically 4 factorial, but I'll leave that alone for a sec. So one thing you should notice is that these factorials will naturally arise in our work due to the derivatives of these polynomials. And so you're going to see them. You're going to see them all over the place. Okay, the last step is then to evaluate all of these polynomials at the center. So I'm evaluating them all at 0. Anything with a variable will just be 0. So you're just going to be left with the a sub 0 in the first case, a sub 1 in the second, 2 a sub 2 in the third, 3 factorial a sub 3, 4 factorial a sub 5, and then finally 5 factorial, 4 factorial a sub 4, and then 5 factorial a sub 5. Okay. Okay, then as promised here in step 2, I need to, well, step 1 and step 2, I'm forcing these equivalences. I need all of this to be true, and that will give me what I should make my coefficients on my polynomial, right? So I need to, what am I equating? I'm equating this guy and this guy, etc. So I'm equating those, and then I'm equating this guy and this guy, etc. Right. Okay, so I have f of 1 is 0, or sorry, f of 0 is 1, and I want that to equal p sub 5 of 0, which is a sub 0. So let me just cut to the chase. I need a sub 0 to be 1. So I got one of them. Then I need f prime of 0, which is 1, to equal p prime of 0, which is a. So that tells me what? That tells me that a is a sub 1, should be a little sub 1, is 1. The next one tells me that 2a sub 2 is equal to 1. In other words, a sub 2 is going to be 1 all over 2. And then 3 factorial a sub 3 is going to be 1. So a sub 3 is going to be 1 all over 3 factorial. And then likewise, 4 factorial a sub 4 needs to be 1. So a sub 4 needs to be 1 over 4 factorial. And then finally, 5 factorial a sub 5 needs to be 1. So I'll have a sub 5 is 1 over 5 factorial. Great. That tells me my polynomial, my 5th degree polynomial representation of the function e to the x is, well, originally, you kind of keep in mind, we had a sub 0 plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed. So I'm replacing a sub 0 with 1. A sub 1 is 1, so I just get 1x, which is x. Note that that thing right there is what we originally got with this kind of recollection example. Okay? And then we amp it up, right? So a sub 2 is 1/2. A sub 3, 1 over 3 factorial. A sub 4 is 1 over 4 factorial. A sub 5 is 1 over 5 factorial. And there it is, okay, in all of its glory. Okay, so how did I get the process? How do I streamline this process and make it general? Well, all you're doing is equating coefficients to the derivatives of the function you're trying to get a representation for, evaluated at the center, right? So a sub 0, so let's just make sure we all are on the same page. In general, A sub 0 should equal f of 0. Okay. If we're presuming this center value is 0, and this is going to be called a Maclaurin polynomial, a sub 1 is going to equal f prime of 0. Okay. A sub 2, well, we got to be a little careful now, right? Because the derivatives of the polynomial cause these coefficients. So it's really not just a sub 2, but it's rather 2a sub 2 equals f double prime of 0. In other words, a sub 2 will be f double prime of 0 all over 2. Then we start spackling on factorial values here. So f triple prime of 0. So a sub 3 will equal f triple prime of 0 all over 3 factorial. And honestly, you could think of 2 is the same as 2 factorial, right? So 2 is the same. Well, what is 2 factorial? 2 factorial is 2 times 1. So that's really just 2. So if you wanted to, you could write a sub 2 with a factorial right here. And then a sub 1, I mean, honestly, f prime of 0 all over 1 factorial, if you wished. And then a sub 0, you could think of it as being over 0 factorial. So why would I want to do that? It's just so you can see the pattern that's occurring, right? So 4 factorial a sub 4 will be the fourth derivative evaluated at 0. So a sub 4 will be this. And then I think even if we needed to get up to a higher degree, right? What if I needed an nth degree? Well, let's not even go crazy. Let's just say like 8th degree, right? So it would be 8 factorial times a sub 8 equals the 8th derivative evaluated at 0. So a sub 8 would be the 8th derivative evaluated at 0 all over 8 factorial. Excuse me. And then on, and then we could say n factorial in general. A sub n equals the nth derivative evaluated at 0. And so a sub n is going to be the nth derivative evaluated at 0 all over n factorial. So those are our coefficients for our polynomial representation. We could write it p sub n of x. The polynomial representation is just going to be these f of 0 plus f prime of 0 x plus f double prime of 0 all over 2 factorial x squared plus f triple prime of 0 all over 3 factorial x cubed plus blah, 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 plus all the way up to whatever degree you're worried about. Okay. This thing right here is called the Maclaurin polynomial. Okay, so we'll write Maclaurin. And I call it a representation because it's not always going to be the case that it's completely equal. Okay, unless you're approximating another polynomial, you'll get the same thing back, right? But in other cases, it probably won't be the same thing. So representation. The other guy, the Taylor one that they talk about, really isn't all that different. The big difference is that it's centered at a different location. Okay, so it's not centered at 0. And that's not a big deal. So let's write C is 0 in that case, and then here C is not 0. The only difference is that the entire polynomial is shifted. So if you remember your sections on graphing functions, you could graph x squared like this. That's just x squared. Y equals x squared. But then if you wanted to shift it over, what would you do? So maybe I shifted it over here to 1. I would write y equals, replace x with x minus 1 squared, right? Okay, so that's the idea when you do this Taylor polynomial. We'll have to rewrite 0 as just plain old C, but you got to be careful. Instead of writing x, you have to write x minus c because it's all shifted over. Okay? But other than that, it's the same old baloney. I don't know why they make such a big deal out of, hey, let's give everybody a special name, even though they're kind of just subcases of this special case. I don't know. Just trying to make your life worse, I guess. Enjoy it. And yes, you should have these forms, this form memorized, okay, in case you're wondering. Okay, so let's go ahead and build some of these. Number 1 in the homework looks like it's actually a Taylor. It's not centered at 0, so it's a Taylor. Be careful. Let's try number 2, because that's very similar to what we were just doing. So we'll say building a Maclaurin. And the process will kind of be a lot like what we did here in this big long example, except you're not going to need to do the polynomial part. What you're going to end up doing is just this part of it. Okay? And then you substitute into the Maclaurin polynomial form. Okay? So we need to do this. Okay. So build Maclaurin, we're going to do number 2, which is f of x equals e to the negative x. And we want to do a 5th degree Maclaurin. Okay? Okay, so you just start with e to the negative x and then get all of its derivatives up to the 5th degree. And this is going to test how well you know how to do derivatives and how well you can memorize formulas. So the first derivative, e to the negative x times, from the chain rule, the derivative of negative x is negative 1. And the second derivative, e to the negative x, it was already negative, but if you multiply it by another negative because of the chain rule, now it's going to become positive. And then you'll see this alternating effect in the derivatives. Then we need to evaluate all of them at the center. And we're presuming it was centered at 0. It said find the nth Maclaurin. So Maclaurin means centered at 0. Okay? So e to the 0 is 1. E to the negative 0 is just e to the 0, which is 1. And it looks like these will be alternating as well. So f prime of 0 is negative 1. Double prime of 0 is back to 1, etc. Okay, so for the polynomial, 5th degree polynomial, I like to think of it in like boxes, so I'm just filling in the boxes, right? So this will be x and then blank x squared over 2 factorial, x cubed over 3 factorial. Filling in blanks for some reason just makes everything in my life easier. It relaxes me. Okay, and then you're copying and pasting, right? You're just going to take this column and copy and paste it into the boxes. And if you feel ambitious enough, go ahead and simplify it. Okay. Okay, let's try another guy. Well, yeah, sure. Let's do another one. So this is number 4 in the homework. So f of x equals 3 cosine of pi x, and we want a 4th degree approximation. So again, I have to go f of x, f prime of x, f double prime of x, f triple prime of x, and then f 4th prime, 4th derivative. Okay, so how well do you know how to take derivatives? The derivative of cosine is negative sine, and then I have to do a chain rule on the guts, so that'll give me a factor of pi. So it'll be negative 3 pi sine of pi x. Derivative sign is cosine. And then from the chain rule, you get another factor of pi. So I'll have negative 3 pi squared. Derivative cosine negative sign. So that will turn that expression positive, and then you get another factor of pi. And then finally, the derivative of sine is cosine. Chain rule, another factor of pi. Now I go through and evaluate it. This is Maclaurin, so it's all going to be at 0. Plugging in 0, cosine of 0 is 1, so this will be 3. This will be 0, negative 3 pi squared. This will be 0, 3 pi to the 4th. And then we go to our Maclaurin polynomial. I need P4 of x, so it'll be blank plus blank x plus blank x squared over 2 factorial plus blank x cubed over 3 factorial plus blank x to the 4th over 4 factorial, then copy and paste. Okay, clean her up. Okay, let's give you a quiz. Let's make it a little bit easier. And, well, no, let's keep it kind of the same spiel. This time, let's do 3 sine of pi x. So you need the 4th degree Maclaurin polynomial for 3 sine of pi x. Okay, so the n value here will be 4. Pause the video and you can scribble that out. When you go through it, you're going to find it's not truly a degree 4, and that kind of causes issues sometimes in some of the homework problems. Don't overthink it too much. In this case, your quiz answer should be degree 3. Okay, let's move on. Building a Taylor. So we built some Maclaurins. Let's go ahead and build some Taylors. So here C, of course, is not 0. And let's go at it. So number 7, we want to find an approximation or representation for the ln of x, degree 4, centered at 2. Okay. Same process. So you get f of x, and then its derivatives to the 4th derivative. This is 1 over x, but for the sake of my sanity, let's write it as x to the negative 1. Let's be at negative x to the negative 2. I'm going to rewrite it as 3 factorial. Evaluate. This will be ln of 2. This will be 1/2, negative 1 over 2 squared, 2 all over 2 cubed, and then negative 3 factorial all over 2 to the 4th. Again, I'm not crazy about multiplying stuff out. Again, it's for pattern recognition, but not only that, it makes stuff easier to simplify, in my opinion. So anyways, here we go. Box plus box. And here you got to be a little careful. It's x minus c, right? It's a shifted version of the Maclaurin, basically. So plus x. 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 Copy and paste. One thing I'm noticing is this is kind of you know, you can think, again, you think of 2 as 2 factorial. So what you're saying in these later terms are like n factorial all over n plus 1 factorial. And in those cases, you could simplify that, right? This is n times n minus 1, n minus 2, blah, 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 3 times 2 times 1, all over n plus 1 times n minus 1, blah, 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 3 times 2 times 1. This all cancels, and you got 1 over n plus 1. So stuff like 2 factorial all over 3 factorial, that's just going to equal 1 over 3. And the next term we had 3 factorial all over 4 factorial, that's just going to be 1 over 4. So hopefully that's kind of clear. So let's go through and try to make it look pretty. I'm not even going to multiply out the denominators. Again, it's a matter of kind of recognizing patterns. And it's probably been better not to write 2 cubed, just rather write 2 squared times 2. And then this next term would be 2 cubed times 3 factorial minus x minus 2 to the 4th all over 2 to the 4th. Oops, those factorials are canceling out, sorry. Times 4 factorial. Just 4. So why would I care? It's because eventually we want to put this stuff in the summation notation, and this is going to help you identify the form. Here we wouldn't really bother, but if I wanted to write it, it would be ln of 2 plus the sum from n equals 1 to 4 of x minus 2 to the n all over 2 to the n times n. Right. So having it kind of split apart and not multiplying it out, again, I don't know how to sell you on this idea. It's important. You're going to want to be able to do that eventually. Okay? Once we get into the actual series, which are the infinite versions of what we're dealing with right now. Okay. Then we'll have to convert it into summations, and we'll be super interested in knowing, you know, where these things converge and where they diverge. Okay. So there's our first example. Let's look at Taylor's theorem. Okay, so how good are these things with regards to approximation, right? So I was kind of calling them representations because I don't want to say they're exactly the same as the function you have based them upon. Okay, how good are they? So how good are they? Well, it comes down to this thing called Taylor's theorem, and we don't really see it proven until you get into later maths. Probably in your, so maybe advanced calculus, you would get it, maybe not even there, maybe real analysis. You got to wait till real analysis just to prove Taylor's theorem. And I don't even think they always do it. But it seems like it's based off some weird mean value theorem, maybe a higher dimensional version of it. But it has been years since I saw it, and I only saw it once. So just take my word for it. It's probably a little out of our wheelbox, or at least it's out of my wheelbox. Get somebody at the university to help you. All right, but here it is. Okay, so the difference between f of x and the nth degree polynomial that we've built off of f of x, we're going to call that thing the absolute value of this remainder function r sub n of x, and we're going to say it's bounded above, and it's a little bit like the alternating series estimation theorem. It's going to be bounded up above by kind of the next term in your polynomial. Right, so looking at the general term of the polynomial back here in Taylor land, in these Taylor polynomial representations, if I were to kind of extrapolate to what I would think the next term would be, it would be the n plus first derivative evaluated at c all over n plus 1 factorial times x minus c to the n plus 1. It's going to have that flavor to it. The problem is we're going to have to kind of replace this thing with some maximum function, okay, for the theorem to pan out. So what is it then? Well, it's going to be, and it's going to look a little weird, but it will look like kind of like I was saying, it's kind of like the next term in line. Okay, so anyways, what is it? Well, it's going to be the max value of the n plus first derivative on this interval that you care about, which the interval is going from the center to whatever value you're approximating, and it could be from c to the x or x to c. And we're dealing with absolute values because all this junk is in this absolute value. And then this will be all over n plus 1 factorial, and then times the absolute value of x minus c to the n plus first power. Okay? Okay. And that's a lot to swallow. When I first saw that thing, I was like, what the heck is that? You know, it's coming down from Mount Olympus, basically. Like I said, it has, you know, there's things in there that you probably wouldn't learn until later in math, in the math universe. But anyways, let's try to make some of this a little bit easier for you. When you're looking for this max value of this n plus first derivative on this interval, there's usually two cases or maybe three cases. The first case is if you're dealing with cosine or sine functions. So you'll let it equal 1 if you're dealing with a function f of x equaling cosine or sine or some variation of those. Okay, and why is that? It's because the cosine and sine functions are always bounded above and below by by 1, right? So its max is at 1, its min is at -1, so it's bounded above by 1. Okay, the next one that we'll say is e to the x, which is a bit silly. It's like you're trying to do an approximation of e to the x, but you're using e to the x to do that approximation. I don't know. Okay. So I just put e to the x there. And what else? If it's something else, there's going to be some work, okay? Otherwise, you may be tasked with actually figuring out how do I maximize this n plus first derivative on this interval, okay? And basically, you find the absolute value of the n plus first derivative, and then look for critical numbers, etc. Okay, so actually, you kind of think of this thing as a function unto itself. So you kind of like find what's called g of x, which is the absolute value of the n plus first derivative, and then you get the g prime of x. So take g prime of x and maximize it. Okay. But thankfully, that doesn't come up very much, so I don't even think it comes up in the homework that we dealt with. But okay, well, let's look at number 8. And what we're trying to do is, and there's two types of problems again. There's how good is my approximation, and then secondly, how many terms do I need in order to get so good of an approximation? We saw those two kinds of questions when we dealt with the alternating series estimation theorem back in section 9 whatever. Okay, so anyways, cosine of 0.7, and the homework, what they're going to do, am I recording? Please tell me I'm recording. Yes. Okay. So this is number 7. No, it's number 8. Okay. So they're basically saying, okay, I'm approximating cosine of 0. In this case, their problem is 0.6 with a 4th degree polynomial. Okay, so we have this thing's, it's 1 minus, and if you were to figure out the actual, you know, the Maclaurin series version of it, the Maclaurin polynomial version, it would be 1 minus x squared over 2 factorial plus x to the 4th all over 4 factorial. But here what we're doing is actually doing an approximation by substitution. And this looks even more familiar to what we've been doing, because it just gives you kind of the first couple terms of a series, right? Okay, so anyways, we want to know how good of an approximation this is, so we're going to use Taylor's theorem. And Taylor's theorem, if you look at the theorem, there's a lot of unknowns here, okay? There's actually 4 kind of unknowns. So we're working with this R function of something. Okay, so the center value is at 0. It doesn't say it in the problem, but it is Maclaurin. You can tell by the form of these 3 terms. It's not x minus something, right? Then secondly, there's the x value itself. What value are we trying to approximate? What x value? In this case, it's 0.7. The other unknown is n. I haven't filled it in, but in the Taylor's theorem, the n is the degree of the polynomial. Okay, so in our case, it's degree 4. It's just the highest exponent. Okay, so I can start filling in a little bit of my function notation there. This is degree 4. And then finally, the last thing is a stupid maximum of the n plus first derivative on this interval from, in this case, it'll be from 0 to 0.7. Okay. Fortunately for this case, it is just this cosine function. Okay, so we're just going to say 1. Okay, and that's kind of, you know, the deal. You'll go through these 4 things, figure out what they are, and then populate your remainder theorem. So this will be less than or equal to 1 all over n plus 1 factorial, which will be 5 factorial. I'm replacing that big max n plus first derivative that you see above with 1. You just replace this thing with 1. And then that's all over n plus 1 factorial, so 4 plus 1 is 5. And then times the absolute value of x minus c, so that'll be 0.7 minus 0. So you can see the formula above. Raised to the n plus first power, so again, that will be 5. Okay. The homework is asking for 3 significant digits. What does that mean? That means start counting digits after you go through the 0 positions. So here, don't count this, don't count this. And then as soon as you see a non-zero term, start counting numbers. Okay. So that would be 3 significant digits right there. Okie dokie. So it's a pretty good estimation. And then they want you to actually, so in this next part, which is all, these problems aren't written very well, what exactly is R sub 4? Okay, and that's just going back to this definition. It is the difference between the polynomial evaluated there and the function evaluated there. So we don't want to put the 1 over 5 factorial thing. That's just an upper bound for the remainder. We now want to figure out what exactly is R sub 4 of 0.7. Okay, and I'm going to put this in absolute values and make sure it's positive. I have cosine of 0.7 minus 1 minus 0.7 squared all over 2 factorial plus 0.7 to the 4th all over 4 factorial. And I'm actually going to use my calculator to figure these out. Make sure you're in radians. Okay. And again, 3 significant digits, so I don't count any of the zeros and then start counting when I see some numbers, right? So there again, 3 significant digits, and that'll do it. Okay, let's look at number 11, where we have kind of the other type of problem. So in the first problem, we are given a 4th degree polynomial for it. We want to know how good the approximation is. Now we are given a function and an error, and we need to build a polynomial, so we need to figure out the n value. Okay, so here f of x is e to the x. I need f of 0.4, and I want my error, the difference between the polynomial and the actual function, to be less than 0.001. Okay, so again, I'm going to go to this R sub n formula, and I got to get this information, x, c, and this max thingamajig. The n value, I don't know. The x value, I want to approximate at is 0.4. The c value, the center, it's I don't know if they note it in the problem, but it should be 0. It's just Maclaurin. Basically, you could determine that based off kind of where you're approximating at. So if you were trying to figure out f of 20, you would not locate it at 0. Okay, you would want to move it over to some familiar value close to 20. Okay? If we're approximating 0.4, you want to keep the x value close to 0.4. So 0 is kind of the natural value for C. Okay, then finally the n plus first derivative on this interval. So what is the interval? I'm going from the center over to the point where I want to approximate it at. The exponential function is increasing, so I'm going to say this is less than or equal to, or let's just make this equal to, so the max is equal to the function evaluated at the right endpoint. Okay, this is a bit kind of, I don't know, cheap, because you don't know what e to the 0.4 is, but here you are using e to the 0.4. So there must be some flaw in my thinking that I'm just not picking up on, because I don't know. I mean, I'm getting older. Is that it? I don't know. Okay, so anyways, we'll fill in the blanks. So I'm replacing that max value with e to the 0.4. That'll be all over n plus 1 factorial. I mean, a lot of times back in the day when they wanted me to do these approximations with exponentials, I would just use the number 3, because I know e to the x, is kind of 2.7 something. So I could always bound it above by 3 to the x. But I don't know. Okay, so anyways, I'll have 0.4 and then times, I usually don't put these kind of problems on the test either. 0.4 to the, I don't know what the n value is, so just put n plus 1. So that's x minus 0, 0.4 minus 0, absolute value of 0.4 minus 0 is 0.4. And then raised to the n plus first power, I need that to be less than 0.001. Okay. So I have e to the 0.4 all over n plus 1 factorial times 0.4 to the n plus 1. I'm not going to be able to solve that inequality, right? Not given the meager tools of existence I've been given by my university education, I'm not going to be able to solve this inequality. So what I'm going to do instead is just trial and error. And I'm going to just plug in some n values, right? So I'll start at n equals 1. And then I'm going to go to my calculator and get some numbers here. Let me make my mode correct before I even start. Okay, so what do I got? E to the 0.4 divided by 2 times 0.4 to the second power. So that's not going to be good enough. That's 0.1193. So I go to n equals 2. And hopefully I can just fill in this junk. Okay, 2. So this will be 3 factorial 6. So 0.0159er, still not good enough. Okay, 3 times 2 is then 24. I'm getting close, 0.0015901. And 4 should do it. I think 5 factorial is 120. Yeah, okay, so 0.000127. I'm plugging that into this formula, okay? If you're wondering, I'm taking like n equals 1, plugging that into there. Then I'm taking n equals 2, plugging that into there, and that's where I'm getting these numbers, so 0.00 whatever. And as soon as I get one that's less than 0.001, that tells me the length of my polynomial. So here I need a degree 4. Okay. Okay, so I think that will get you through the homework more or less. We'll call it quits there. Thank you for watching, and I will see you later.